right. Not a bad turnout. I mean, I expected a lot more in the ecology class since I was passing back exams.
Where is everybody?
I don't know. I'm just right now. Let's see. We're live. I can't believe Zoe is not on the live stream right now. She's probably enjoying it in Epcot. No, we have is that honors conference? Is that what it is? I don't know where people are. Anyways, we're plugging ahead. So we did one sample t-test. Did I show a homework assignment? Did I show it? Oh. Okay. I'm gonna post this. Yeah, we're gonna post this. This is what I am meant to do. Make available. Come on. I was going to update this. That's what I forgot to do. So I'm gonna update it and have it set up so what we can do is have you type in the answers. All right. Oh, hold on. Yeah, you can't see this. There it is. It's available. So it's up now, and I meant to do it because this was perform the test and answer the question, and then use R to obtain the p-value. Well, we're using R to get our p-values, so we don't have to do this. You are already using R. Key thing for us is choosing the test. Are we going to do a t-test or a z-test for each of these questions, and then actually running the test? All right, so our exam will we'll have two different parts to questions like this. So we'll have a section on the exam where I give the question, and then you just tell me, is this a t-test or is this a z-test? So knowing which test to use. And then there's going to be a separate part where you'll have the question, and I'll tell you, use a t-test to answer this question, or use a z-test to answer this question. Because what I don't want to do is like one of these questions. Say you say this is supposed to be a t-test, and you run the t-test and you get the p-value. Well, that was the wrong test, perhaps.
You get the whole thing.
Yeah, you get the whole thing wrong because you ran the wrong test. So I've kind of separated it, just like we did with the binomial Poisson distributions, where I said, okay, which distribution would you use? Binomial or Poisson. And then next part, and we'll get to this part, test to see if we're random, and then you have to use the correct distribution to generate your expected value so that you could then run your chi-square test. So it's in those questions I'll say use the Poisson distribution to get your expected values and determine is this population randomly distributed or whatever. So we'll get a first homework. It'll be set up not as like an assignment that you upload, but more as like a homework quiz. The first part will be just these 5 questions, and you're going to mark t-test or z-test, and we're going to have that due on Monday. So that way we can answer any questions as to why is it a z-test or why is it a t-test, and then we'll have the rest of it actually calculating the stuff, the p-values, actually performing the test. We'll have that due probably on by Wednesday, by that Wednesday class. So on Monday I want to be able to address, are we picking the correct test? And then you have Monday and Tuesday to actually do the tests. All right. So look at these, and then start reviewing it, because we just finished the t-tests, and we did the z-test and we did the t-test by hand, which was basically taking the values, using the pt function or the p-norm function to generate our p-value, and then we interpreted that result to come up with a conclusion or interpretation, and do all of our reporting. So one sample t-test, we use it to answer the same types of questions that we would use the z-test for. All right. So we're testing, is a sample mean equal to some given value, some given mean, or to a population mean? But the difference between our t-test and the z-test comes down to that standard deviation. If we have a population standard deviation, we do the z-test. If we have a sample standard deviation, we use the z-test. I'm sorry, z-test if we have the population. The sample, we use our t-test. The assumptions of this test, of the t-test, is that the data are random and independent, and the data are normally distributed. All right, these are our two assumptions. We normally have to check our assumptions before performing the test, but up to now, I've just said assume that all of our assumptions are met. All right, how do we use it? Well, we can use our t-tables to get our t-observed and t-critical values. We know how to do that, but what we're going to use, so know the idea. If I give you a t-critical value and the t-observed, know how to interpret those, but we're going to use R and the pt function to get our p-values. And then when we report it, we report our conclusion or the interpretation, our test statistic, degrees of freedom, and p-value. So our t-test is one of those where we report all 5 values. And then our degrees of freedom could be reported as either df equals, or we can use degrees of freedom as a subscript to our test statistic. Now, when will we encounter these types of problems, like the homework problems? You'll see it on exams. That's when you see it. Very rarely will you actually work with data like that, because if you're going to work with the data, you yourself have collected those data. So we have a vector of data. There's really no point to calculate means and standard errors and do this longhand when R can do all of this for us. So what we're going to do is we're going to run this code, setc databack. All right. So go ahead and run it. Get it in R. So I am just going to take my R. So this is still one sample test. We just finished our examples. So I'm going to create a new header. So t-test using data vectors. All right, so that's what I'm going to mark it. So generating the data. And then I'm going to move this over and copy this code that I told you to generate. And make sure you run it so that we actually have dat-vec. Yep.
So on my R, if I close it out and reopen it doesn't like the chunk doesn't highlight and allow me to run it.
Yep, I do. Go File, Save As. At the end of that, at the end of your data, it's not hard. For some reason, it's only reading it in as a text file. When it has the RMD, it knows it's an R markdown and does the highlighting.
I went the long way and like copied and pasted everything last time.
Oh.
Into a file.
You could have emailed me on that.
Sorry.
That took me a while to figure out. Once we started using the markdown, I had no idea. I spent quite a bit of time trying to figure out what is going on. I did the same thing, copy and paste it.
Yeah.
It's like, what is going on?
Yeah.
Doesn't always happen.
No. It just started it. Like I was like, I didn't do anything differently, I don't think, but maybe.
I think maybe when you use the dot and then data, period, and then the data, that may have thrown it off. All right, so did we run the data? So what does this function do? What do we have here? What is data vec or dat vec? It's a vector of what? Random data from a normal distribution. How many? 18. All right. What's our normal distribution that it was drawn from? Mean of 33, standard deviation of 2.22. So that our vector should reflect this distribution. And then what do we do? This is the last part. Yeah, we rounded to two decimal places. All right. So that's what we pulled from. If we calculate the mean of this stat vec, it'll be close to 33. Might not be exact, but it'll be close to 33. All right. So our question that we're going to work with is, does this vector have a mean of 31? All right, that's what we're testing against. Now, we drew it from 33. But every time we draw this vector, we're going to get a slightly different sample, and it's going to give us a different mean. All right. So if we had a sample size of 5, we're probably going to see a lot more variation in our mean value than if we did a sample size of, let's say, 100. So if we had a sample size of 100, yeah, our mean of that vector is going to be pretty close to 33. And it's going to have just a little bit of variation. But we chose 18, or I chose 18, to try to give us some measure of variation, of variability. Maybe we have a mean of 31, maybe we don't. So how do we go about doing it? Well, we could do it by hand. We could calculate the mean, we could calculate the standard error, we can pass that to the PT function and get a p-value. That's kind of the long way. Or we can let R do all of that for us. R has this convenient function, t.test, that will do a t-test for us. All right. If we want R to do the t-test for us, we give it the numeric vector. We give it a vector of numbers so that it can calculate the mean, it can calculate standard error, and generate our PT values using the PT function. But we not only have to give it a vector of data points, we also have to say what the hypothesized mean is. What are we testing against? All right. And then we also have to specify if it's two-sided, a two-tailed test, or is it a one-tailed test? Are we saying that our mean is less than our hypothesized mean, or are we saying that it's greater than our hypothesized mean? All right. So what we're testing here is we generated the data, and our example, does dat_vec have a sample mean equal to 31? All right, that's our question. So what's our null and alternate hypotheses? Okay, so I'll say x bar is equal to mu. So we're going to say that they are equal. What's our alternate? Yep, x bar is not equal. So NEQ, not equal. Let's see here. In other ways, you could do, alternative format, exclamation point equals could be used as not equal. All right, so that is in like some of the functions that we would use. If we were trying to select only items that did not match something, we could use that exclamation point equals. All right. Just like I think we do is not. So we have is NA, is dot NA. That may have appeared someplace. We could do exclamation point is dot NA to say that it's not that. Or you could use that format. That could also potentially be used. So I'm using it, so if I script it, or if I knit this, it's going to actually show our not equal sign. It'll show that, but if you wanted to do it that way, that's also possible. All right, so that's what we're asking. It's going to be a two-sided test. So based on the null hypothesis, we are running a two-sided or two-tailed test. All right, and it's a two-tailed test because we don't have a population standard deviation. We're going to have to approximate it using our sample. The function is t.test, lowercase, x, mu, and then alternative. All right, so x, that's our numeric vector. Mu is the hypothesized mean. All right, and then alternative equals two-sided gives two-tailed test. Alternative equals greater is one-tailed when we predict x bar will be greater than mu. An alternative less is a one-tailed test, again, when our x bar is less than the mu. So we're kind of laying it out when we would use each of these. Now, you don't necessarily have to include it. Like the default is two-tailed. All right, that's our default. So we can leave that off, and R will run a two-tailed test for us. I recommend always including an alternative just so you can read your code. And we're going to see how to do a two-sample t-test where we can write it as a formula. So the alternative helps to keep things in order and we're less likely to encounter an error message from R. All right, so let's run the test. Run the test. All right, we have the function. So t.test, our vector is dat_vec. All right, that's our numeric vector. Our hypothesized mean is 31. And we're doing a two-sided test, two-tailed test. So if you run it, you'll get this output. Why that goes blank. All right, so this is the output. So let's see the output. This is the output of a statistical test. We've seen one before, which was the Shapiro-Wilk test. Similar type of output. So it's going to tell us the test that we ran, one sample t-test. It tells us the data that we used to run it. So this was dat_vec. All right, and then it gives us our t. That's our t observed. It gives us the degrees of freedom. It gives us our p-value. Those are the three things that we're most interested in on this test. All right, and then it gives some extra stuff. All right, so it tells us what the alternative hypothesis is. So when we use two-dot-sided, it says that our alternate is that the true mean is not equal to 31. Because we're testing if our sample mean is equal to 31 or not. All right, is it equal? It's not equal. All right, if we did a one-sided test, it would tell us the true mean is greater or less than 31, depends on which one we have. All right, it also tells us the mean of our vector. So that's the mean of dat vec, which we drew from 33. This one's 32.96, we're close. All right, we're testing, is this value close enough to 31 to where we can conclude, yes, it is 31. And then it also generates a 95% confidence interval of our mean. Is this a bootstrapped confidence interval? No. It's a regular confidence interval. How can we calculate that? There's our mean. It's the same as the mean. It's up there. How do we calculate a 95% confidence interval? What's that equation? QT? Times standard error of dat vec. And I don't know if I ran the standard error function or not. No, I didn't. So let me open up my useful functions. What did I call it? Function script. There it is. Open that up, grab my standard error, copy it, paste it into my functions. Now, that's our output. There's our 95% confidence interval. You'll see that they are the same numbers. So in many ways, if we know that we're going to run a t-test, you don't necessarily have to calculate your mean. You don't necessarily have to calculate a confidence interval because it gets reported in our results, in our output. All right? So this is put that as a review. So based on this, we have a write-up. A write-up is our sample mean is not equal to 31. We ran a t-test. T 17, so degrees of freedom, 2.97. So I think we're sufficient to do 2 decimal places. And our P is less than 0.009. So we gave our conclusion, interpretation, test statistic, degrees of freedom, p-value, all fine. Now, why did I conclude that our sample mean is not equal to 31? Why did I make that conclusion? Well, now that's the alternative hypothesis. Hold that thought. So if I use greater, I get this. True mean is greater than 31. And note, our p-value is reduced in half. If I do less, it says true mean is less than this. So this line here is just telling us our alternate hypothesis, doesn't tell us a conclusion. So you said, because the confidence interval doesn't capture 31. You're right. If we are normally distributed, our confidence interval will be symmetric. And if that confidence interval does not capture our hypothesized mean, which is 31, then our t-test should tell us that we are not equal to that value. But why did I make this? How did I know to say that? Yeah, what's our p-value? Where's our p-value on this output? It's less than 0.05. If it's less than 0.05, what do? Yeah, our p-value says we're less than 5% chance that this is true, that we would get our data that we saw, the mean of almost 33, if the population was actually drawn from a mean of 31. So yeah, it's super small. We reject our null hypothesis and thus conclude that, yeah, our mean is not equal to 31. So in a sense, yeah, the alternative hypothesis tells us our conclusion, but it only tells us our conclusion if that p-value is less than 0.05. And if we did the correct two-sided versus one-sided test. All right, so we look at our p-value. That's what we look at. If it's less than 0.05, they're not equal. If it's greater than 0.05, they are equal. And that's what I have up here. Same type of thing. Again, items of interest, p-value, right here, our degrees of freedom, and our t. This, move that, there we go. All right, so there is a data file on Blackboard called mosquitofish.csv. On that file, we have 4 ponds where we measured the length of mosquito fish. All right, so we've got our data, file. What I want you to do is download that file, get it into R, and then answer these questions. So for pond 1, is the mean equal to 24.5? For pond 2, is the mean equal to 25.15? For pond 3, is the mean smaller than 25.05? And for pond 4, is the mean greater than 23.75? All right. So we are going to assume that all of our assumptions are met. So go ahead and download it and start working on this. Make sure you have a write-up to practice the write-up. So I had to change my heading to yes to make sure it reads in as pond 1, pond 2, pond 3, pond 4. Warning, make sure your heading is yes. Yep, to do each one. Figures. What's it? Uh-oh. stopped everything below it from working. And why it didn't just automatically update, I don't know. Right. Is that red? Yes. You need to redo, let's go back up here, change header equals T. And run that. Now, that created 200 observations. Now, instead of V1, V2, V3, V4, it's pond 1, pond 2, pond 3.
I have a question. So, and like when you do the underscores or in the bracket, the reason for your meaning, and then what is the what is that?
That is our T observed value. So if our assumptions are met, our T value, our T observed should follow T distribution. Because if we follow, let's see if I can get this. Let's do this. Go here. Close this. All right, so if we follow the null distribution, then our sample represents just a random sample of our sample mean is just a random sample of that population, and it can change. So I'm just going to go, I'm going to set the C to 1. All right, library car. So I'm just going to do a RDAT. I know that. R norm of, I'm going to do 25, mean of 15, and SD of 2. Something like that. All right. If I calculate the mean of this RDAT, all right, I'm going to get a slightly different value every time. All right. But that doesn't tell us anything because we want to know what's the likelihood that we get the sample that has a sample with, how often is it that we'll get a sample mean of 15 just by random chance alone. And you can see that in this case, it changes. 14.7, 15.2. We get variation because our underlying distribution has standard deviation of 2. We have variation in our population. When we're asking our question, is our mean equal to some value, we have to have some sort of test statistic to test it against, right? And that test statistic is our T distribution. So if I do a T observed value, all right, that is our mean of our DAT, parentheses this, minus our hypothesized mean, let's say 25, all right, divided by our standard deviation, or standard error of the mean. But this is the population, and we don't know that, right? So what we have to use is a standard error of our sample, which would be the standard error of that R DAT. And that comes up with the T obs. So, should we do this? so we've got the mean and the t-obs, and you can see standard error of s over the square root. Yeah. So we don't know what our actual population. Right, standard deviation of 2. Why is that so large? Mean of r dat minus 25 over standard deviation over the square root of sample size. Let's see if we get the same one if I do that. Actually, we'll do square root of the bar of r dat over length 25, 24. We'll hard code it in there. Yeah. So if we actually do sample from this mean, why did I do 25? 15. Our hypothesized mean is 15, what we drew it from. We get this t statistic, t observed, and that's going to vary as well. But that still doesn't tell us anything about what's going to happen. So what we're interested in is what's the likelihood, just by chance alone, that we're going to get an observed t observed, one of these t observed values, that equal or exceed our actual observed value. So just by random chance. So we have this. We can demonstrate that it works. So we have our r dat, right? So I'm going to do something like this. Null distribution, all right? $10,000 values. All right, so what I'm going to do is generate this data. All right, we're drawing it from 25 values from a mean of 15, standard deviation of 2. Right? And then what we want to do is calculate our standard error, or our t observed. But that t observed is going to be my null dist value. There it is. We're just going to do sterr of r dat. And now, I'll show you hist null dist frequency equals plus 10,000 values, 10,000 different randomized samples of size 25. We think it comes from as a mean of 15. This is our null distribution of that t, centered at 0, which is what it should be. All right. How close does it follow? Well, we can use the curve function. dt of x df is 24. Add is t, and color is blue, and line weight is d, is 2. Whoops. Let's rerun this. We'll get a slightly different value. But that's our t distribution. And did we follow it? Well, I loaded the car package. Let's check a QQ plot. Dist t df is 24. It is. It is pretty spot on. So our p-value is, how likely is it that we're going to get a value? Let's see if I can run these back to back. There it goes. How likely is it that we're going to get a value just by random chance alone if this is our actual distribution? So change this and say, what happens if we calculated a mean of 14? Well, a mean of 14, I'm going to make this. So our t observed would then be 14 minus 15 over, we'll say the same standard error. We'll do 2 over the square root of 24. That was our sample size. Negative 2.455. So now we're looking at this part. 2.55 is right about here. That's our observed. Well, how likely is it to get a value as extreme or more extreme? It's beyond this both ways. The area under the curves. So our transformation, we had to transform it back to the 0 0, 1 distribute or zero distribution, so we can calculate these area under the curves, and that's what our t is telling us. The t observed is the test statistic and says, okay, for 20 degree of freedom 24, this is our distribution. This is what our distribution should be just through random chance. But we collected something that's like way out here, pretty small value.
And like what's the probability?
Or worse,
Oh.
or extreme. That's our area.
Yeah.
So yeah, as we redo this, we'll get a bunch of different values, but it's going to be, everything's going to follow that t distribution. So we report the t distribution, or the t value, so that others can look at our data, the t observed, degrees of freedom, and calculate their own p-value, which should be the same that we reported.
So the T is right under the T in there.
Yep. So we're being transparent in our analysis. Because if we just say, well, our sample has a mean of 14, and yeah, this is smaller than 15, somebody's going to say, whoa, why did you conclude that? They need to know the information that allows them to replicate your analysis. And that would be your mean, standard deviation, or measure of dispersion, sample size, because the sample size determines our curve, our t-curve. And we can change it. So if I change this to, instead of a sample size of 25, we'll do a sample size of 5. Now we're changing that. And now we should see, now you're getting much more variation in our data. So that is, I mean, that's what like a degrees of freedom 4 looks like, this curve. But you can see that we're introducing the possibility of violating our assumptions when we have a sample size of 5. Yep. But if we run this again, I bet we'll get slightly different. See? Same type of thing. So, all right, we'll look at the answers to this, but this is what's happening. So as you can almost guess that if we violate our assumptions, yeah, we can just kind of generate our own null distribution through randomization, kind of like this.
But for our t-test, it's always gonna, it's not gonna follow.
For now, we will. We're gonna review how to assess normality. But yeah, for these problems, we're gonna assume that that all assumptions are met. So that when we run the test, we look at this line. These are the numbers we have to report, and then our conclusions based on our p-value. If it's less than 0.05, we know the means are not equal. If it's greater than 0.05, the means are equal. Or we don't reject it. They're probably equal. All right. So we'll look at these in the write-ups on Monday.